Hey guys, Mrs. Thompson here, and today we're going to cover heating curves and cooling curves. It's going to look a little different because I'm going to handwrite these. Yes, you do have to draw them. It might be helpful to have a couple of colors too handy as I'm going to change colors. Alright, so here is a picture of a heating curve for water. You do need to draw this. What is a heating curve? A heating curve is basically a graph of what's going on with a substance over time. And so you take a substance in a container, a closed container, and you heat it, and you see what happens. So we would think that when we heat this over time, the temperature would just gradually go up. But instead, we see this zigzag pattern that happens. And there's a reason for that. We're going to cover the reasons why we see this zigzag pattern. In fact, you're actually going to do this experiment, and hopefully you'll see the same zigzag pattern. All right, so there are 5 segments that you have to know. We're going to number those segments. So 1. And so a segment would be every time it changes in terms of the curve. So from here to here would be 1 segment. From here to here would be the 2nd segment. So hopefully you remember a little bit about geometry. Okay, so this would be segment 3. As it changes, it's a sharp change there. This is segment 4, and this is segment 5. We're only going to look at 5 segment heating curves. Okay. Now, what's going on in each state? Well, in step 1, the first segment, we are heating the solid. Okay, so we're taking the solid sample. In our case, this would be ice, and we're applying heat to it. And it gradually increases in temperature as we apply heat over time. And then something happens, and then it starts to flatten out where the temperature does not change. Since it's flat here, this temperature is not changing. And instead, what's going on is the energy that would normally go into heating it and changing the temperature actually goes into changing the phase, moving the particles away from each other. Okay. And so, at step 2, what we have is we're now melting the solid. So we have melting occurring. And when you have melting occurring, not only do you have solid, but you also have liquid. So in this case, we're going to write S and L for solid and liquid present in the 2nd segment. All right. As soon as all of the solid melts, and now it's liquid, all the particles have moved far enough away from each other that they're in the liquid phase, then we start heating the liquid. So this segment right here, this is all liquid. So we're heating the liquid in step 3. All right, and as you notice, as you go up, what happens is it increases in temperature over time. Great. Then what happens? It flattens out again. And that is because there's another phase change that can happen. The liquid can turn into a gas. We call that vaporization. And in vaporization, what you have is liquid and you have gas. All right. Then in step 5, right here, it's just gas. So after it finishes this segment, now it's just gas, and we're applying heat to that gas. Remember, we're keeping it in a closed container so the gas particles can't escape. So we're heating gas. All right. So some things that you have to know besides that are some temperatures. Since this is water, we should know the freezing point of water, or the melting point, and that occurs right here. So once it's done being a solid and it starts turning into a liquid, that is melting that's happening. So I'm just going to write that here. Solid to liquid is occurring. And we can read the temperature and find the melting point. For water, we know that this is at 0 degrees Celsius. Okay. If this were another substance, we could read the same graph and say, okay, it's whatever this is. So 0 degrees Celsius. So I'd like to make a note of that. We could read that right here. That's the melting point. All right. Next, there's also a boiling point, and the boiling point occurs at the next flat line. So at my flat lines, I have phase changes. And so if I were to take this graph and read over here, okay, I would find the boiling point. I think I said that earlier. Okay, boiling point. And hopefully you remember that the boiling point of water, which is how under Celsius, based a scale, is 100 degrees Celsius. Now remember, this is specific to water. I'm going to write that. That is the boiling point. If this were a different substance, that 100 and 0 would not be true. We'd have to figure out what it is based on the scale that's here. All right. Next, we're going to make a note about what's going on in this direction. Going from left to right over time, we are adding heat, and adding heat is endothermic. So let's go ahead and write that. Endothermic. Okay, I'd like you to add this part to your paper. We're just going to go over the difference between the rises and the plateaus. So where's the curve rising and where is there a flat point? Where's the plateau? All right, so let's see. What's going on where it's rising is you see a change in temperature. So this could start at something like, let's say in this graph right here, let's say it started at negative 30 degrees Celsius. It doesn't have to be negative 30, it could be anything, negative something. All right, because it's less than 0. Okay, so let's say we're starting here, it's rising. It's increasing in temperature as it goes from negative 30 to 0. So temperature is changing. So there are a couple places where temperature changes. Here, here, and here. So when it's rising, what we see is a change in temperature. Okay, what is going on as it's changing in temperature is all of the heat that's being added is going into increasing the temperature of that substance. So we'll write that. Heat added speeds up the molecules. Okay, so the heat that's added is going into speeding up the molecules. All right, what about the plateaus? Well, in the plateaus, it's flat. There is no change in temperature. Okay, no change in temperature whatsoever. So we're going to write no change in temperature. And so instead of going in, the heat added going into speeding up the particles, because they're not changing temperature, they're not speeding up. So what's happening is they're going into making those particles move away from each other, making them separate. So it says heat added just goes into separating molecules. All right. So in terms of energy, we talked about energy before as being either kinetic energy or potential energy. Kinetic energy as in movement. So when is the kinetic energy changing in this graph? Well, that's any time that the temperature is changing. So I'm going to write that. What's going on as temperature changes is that the kinetic energy is increasing. And let's just put that on our graph. So right here, you have a change in kinetic energy, and same thing here. and here. Okay. When do you not have a change in kinetic energy? Well, you have no change in kinetic energy at any plateau when it's changing phase. So what's going on instead is they're separating and they're changing in what we call potential energy because of their distance between the particles. So delta PE changes at any plateau. Changes in potential energy because they're moving away from each other. So we'll make that. At the plateaus, potential energy is increasing. All right. I want to show you the difference between the graphs in terms of the length of the solid to liquid curve and the length of the liquid to gas curve. Hopefully you drew this like I did, but it's intentionally drawn so that this segment is smaller than this segment. Okay. Why? Because remember that the distance between solid and liquid, that's really small. So very little energy has to go into it to make them move because there's not as much space that has to be achieved. In the liquid to gas, however, there's a lot of distance. The liquid particles have to move far away from each other in order to turn into gas particles. So more energy is required, and therefore a longer line is on this graph. So it says liquid to gas line is longer than solid to liquid line because more energy is needed. So more energy is going into separating the particles. All right. Next, you're going to draw this curve. Cooling curve for water. Now the cooling curve for water is just the same as the heating curve for water, except for it goes in the opposite direction. Okay, it starts out as gas way up there at the top. So we'll draw a line. Okay, then it condenses. Okay, then we have a flat line, and then it goes like this. Small little liquid to solid line up here. So we still have our 5 segments. We still have 2 flat lines and 3 diagonal lines. Okay. So a couple things that we need to know from here is where's the solid, liquid, gas. So it starts out as gas, goes from gas to liquid, then it goes to a liquid, this line. Then it goes from liquid to solid. It's the exact opposite as the heating curve. And then this segment right here is solid. This is still coming. Okay. What is going on in terms of phase changes? Well, from gas to liquid, we call that condensation. Okay. And where is that happening? Well, that's happening right here. And that's flat line. If we were to read this temperature, this would read 100 degrees Celsius. Okay? Condensation and boiling or vaporization happen at the same temperature, just in opposite directions. So here we go. It says water boils and condenses at 100 degrees Celsius. Okay. This little line right here, that's liquid to solid, that's freezing. Okay, and freezing happens, we read this line here, our graph would say 0 degrees Celsius. And so water melts and it freezes at 0. Okay. If we had a different substance, we would read the boiling point and the melting point using this same looking graph. we would read what temperature it is right here for the freezing point or melting point. And then up here we'd read the top graph for the condensation point or vaporization point, boiling point. All right. So it says they can be found by reading the temperature at the plateaus. Remember, those are just flat regions. All right, so we'll get more in depth with these as we do calculations involving heating and cooling curves. So hopefully we can get some practice. See you next time.